Good afternoon, friends, and welcome to again another chapter of physics. Today we are going to study forces on charged particles in electric and magnetic fields. We are going to study forces on charged particles in electric and magnetic fields. So this is a very important chapter in physics. So I would request you to please go through this video in a very slow manner so that you can understand the logic, because this is a completely logical chapter and so you have to go through it very slowly. Please pause with me and then keep doing along with me. I have completed the full syllabus of this particular chapter, so there is no need to make any notes of your own. You don't have to make any notes of your own. Just keep following Parijat sir classes. This is Parijat sir classes. Keep following Parijat sir classes and like, share and subscribe my channel. Like, share and subscribe my channel as much as possible so that I can make more and more videos for you. So this is the main thing what I will be requesting you. So let's get started with the chapter forces on charged particle in electric and magnetic fields. Okay, so friends, let's see one thing. That is, first of all, please watch one thing. What we are going to study, the first topic is motion of charged particle in uniform electric field. That means we will give an electric field and then we will move a charged particle in that electric field and we will note how it behaves. Okay, we will provide an uniform electric field. Then we will move a charge. I will be moving a charge through the electric field. So watch here. This is the x-axis. Please keep watching very nicely, that this is the electric field which we are providing along the y-axis. So electric field is provided along the y-axis, uniform electric field. As you can see that this is a positive plate, this is a negative plate. So electric field is from along the y-axis. Now I am making a charge enter along the x-axis. I am making a charge enter along the x-axis. The charge is plus q, mass is m, and velocity is v. So watch here. So the particle is entering with a velocity v, its charge is plus q and mass is m, correct? So watch here. The moment the charged particle enters the electric field, it starts to suffer a force. Watch here. It starts to suffer a force along the y-axis. It will suffer a force along the y-axis. So due to which the motion of the particle will follow this path. The force of the electric field will start to act on the particle, which will make the particle move up. That means accelerate up. The particle will accelerate up. Okay. So there will be an acceleration of the particle because there will be a force acting due to the electric field. A force will act on the charged particle. It will make the particle move up. So as you can see that as long as the particle was in the electric field, see, this much is the deviation of the path of the particle from the original direction. This was the original direction of the particle. So the particle has deviated this much. Let it be y. Now the moment it comes outside the electric field, the force is again 0. Electric force is 0. And so the particle will follow a straight line. This is a straight line. Please watch. this is a straight line. Okay, so as long as the particle is within the electric field, it will experience a force due to which the particle's path will change like this. It will show a, what type of path is it? What type of path? It is a parabolic path. It is a parabolic path. So let's study here how it happens. Okay, so since there is a force acting along the, so first of all let us take it like this, let the electric field be acting along over a length of x, over a length of x. As you can see, the length of the plate, the plate length is x, so electric field will act along the length of the plates. That means from here to here, the horizontal component, the particle will have two velocities. One is horizontal velocity and one is a vertical velocity. Now initially the particle was having no vertical velocity and horizontal velocity was v. Okay, so how much time does the particle take to travel the horizontal distance? It will be this. The time taken to travel the horizontal distance will be this. In that same time, the particle will also move up. In that same time, the particle has to move up. Clear? So let the vertical displacement be y. So now we know there is a force acting due to the electric field. So what is the force due to the electric field? This is the force acting due to the electric field on the particle along the y-axis. Okay, so what is the acceleration? Acceleration is force by mass. This is the acceleration. That means as the particle will move forward, it will accelerate along the y-axis. Clear? So now using this equation, the vertical displacement is y. Initial vertical velocity was 0. Initial vertical velocity was 0. So this is 0. Plus half into the a is this acceleration, into the t. What is the t? This is the t, x by v. So creating the equation, you can see we can write like this: x square equal to this into y, and this part is a constant which is called k. This part is a constant. That means x square is coming proportional to y. And remember, when you have this is the equation of a parabola. So we can say that the particle moves in a parabolic path. We can say that the particle is moving, the particle moves on a parabolic path. So what is the shape of the path of a particle moving in an electric field? Parabolic path. The shape of the particle moving in an electric field will be parabolic path. Now outside the electric field, there will be no force acting, so the particle will move in a straight path. The particle will cover a straight path. This is often asked, that outside the electric field, what is the nature of the path? It is a straight path. Within the electric field, the particle will cover a parabolic path. These are very, very important. Please note, these are very, very important things. So if the particle is at rest, please see, if the particle is at rest or moving along E, that means if it is moving along like this, or the particle is at rest, that means, remember, it experiences a force QE because it is moving along E, so it will experience a force QE along E, and hence the particle is accelerated along E because electric field is acting up. Electric field is acting up, and if the particle is moving like this, that means it will suffer a force which is Q into E, and because there is a force, so there will be an acceleration of the particle. Okay. Second, if Q is moving opposite to E, suppose this is the direction of E and the particle moves like this, that means it experiences a force minus QE, remember, and hence it is retarded. Very, very important. If it moves opposite to E, it will be retarded. If Q moves perpendicular to E, that means if this is the direction of E and the particle is moving like this, it describes a parabolic path. Just now we have seen that if the particle is moving perpendicular to the electric field, it will describe a parabolic path. It will describe a parabolic path. Clear? Okay. Now we have seen electric field. Now what we are going to see? We are going to see how the particle will behave in a magnetic field. How the particle is behaving in a magnetic field. That is our target. So please watch here. As you can see from the figure, see, this is the direction of the magnetic field. This is the direction of the magnetic field. Please watch here. The magnetic field acts like this, and magnetic field is represented as B. Please watch here. Magnetic field is represented as B. Electric field is represented as E. So let the same charge is entering the magnetic field with a velocity same, making an angle theta with the direction of the magnetic field. So this is how the particle is entering, making an angle theta. Making an angle theta. See, it is moving with a velocity v, making an angle theta with the direction of b. Making an angle theta with the direction of b. So it will have two components. One is v cos theta, the horizontal component, and v sin theta, the vertical component. Okay. So let's now see here. So V cos theta is the horizontal component along the magnetic field, and V sin theta is in the perpendicular to the magnetic field. Okay. So what is the force acting? Force acting is always, remember, please remember, force acting will be perpendicular to both V and B. The force acting will always be perpendicular to both V and B. Please note here. So that is why the equation comes F equal to Q V cross B. What is V2? V2 is the V sin theta. Okay. This is the V2 because I need the perpendicular component. So this is the force. This is the force. This is the perpendicular component of the velocity, and this is the magnetic field. So as you can see here, that means the force will act perpendicular to the magnetic field. So we will take F equal to Q V cross B, which is Q V B sin theta. So this is the force acting due to the magnetic field. Please keep note, this is the force acting due to the magnetic field. Okay, this is the force acting due to the magnetic field. Okay, next, as I told you that the direction of the force is perpendicular to the plane containing V and B. As you can see, this is the plane containing V and B. So the force is perpendicular to the plane of V and B. Clear? No work is done by this force. Please note here, no work is done by this force. It only changes the direction of motion of the particle. It only changes the direction of motion of the particle. Now the particle, this is the V sin theta. Okay, so F, as you can see that this is the, so as you can see, this is the V sin theta, this is the B. So what happens is that when a force is acting, that means the particle will start to move in a helical path. The particle will start to move in a helical path like this. Okay, now because this is a circular path, so that is why we tell because this is a circular path, so that is why we tell no work is done by this force. As we all know that in a circular path no work is done by any force. Please remember it. Okay, in a circular motion no work is done. So the particle here is actually showing a helical path. As you can see, this is the helical path. This is the helical path. The particle is moving in a helical path. This is called helix. Circular motion but making a helical path. Okay, making a helical path. So here what we will tell, the force on the charged particle provides the centripetal force necessary. Now because there is a circular motion here, as you can see, circular motion. Okay, so this force is providing the centripetal force. So please watch here, this is the formula. This force provides the centripetal force of the for the particle to move in a helical path. This force is the this magnetic force provides the centripetal force. Okay, so from here we get V sin theta equal to BQR by M. Angular velocity, we know that angular velocity, as we all know, omega is V by R, so it should be V sin theta by R. Okay, which is BQ by M. Similarly, frequency of rotation is omega by 2 pi, which is this, and time period of rotation is opposite of frequency, which is this. Now here please, which is 2 pi M by BQ. Okay, so these are the different small formulas which we require here. You can see here, thus all charged particles moving perpendicular to a magnetic field will take same time. As you can see, this is a constant. It is 2 pi M by BQ. Everything is constant here. So we can tell that in a magnetic field all the charged particles will take the same time period, because in the time period formula it is a constant. This part is a constant, so it will take the same time period. Clear? Next, see the horizontal component, as we saw here. Please watch here. So this is the horizontal component. This is the horizontal component, as you can see, V cos theta, and this is the vertical component, V sin theta. Okay, so the horizontal component V cos theta of the particle will have no force acting due to the magnetic field, because I told you only vertical component, only V sin theta will have the force. Only V sin theta will have the force. So V cos theta will have no force. Thus the linear distance traveled by the particle will be constant speed, because there is no force acting along V cos theta. No force, so zero acceleration. That is, V should be constant. That means its horizontal component of the velocity will remain constant. Okay, and the vertical component of the velocity V sin theta will have force. It will have force acting on it. It will have acceleration acting on it. Okay, so that is why, because it will have speed increasing, speed will go on increasing, and that is why it follows this path. It rises like this. Okay, so under the effect of these two, horizontal component and vertical component, the particle covers a helical path, because there are two types of velocities acting. One is V cos theta, one is V sin theta. So the particle will follow the helical path. Okay, so here the linear distance covered by the particle, so linear distance will be covered by the component of the cos theta, V cos theta, V cos theta into t, and t is a constant, we know that. So this is the distance covered by the particle in the horizontal direction, that is the linear direction. Clear? Okay friends, let's see now. If V is 0, so as we all know that F is equal to BQV sine theta. So if V is 0, the force is 0. If the particle moves parallel to B, that means theta is 0. If the particle is moving parallel to B, this is the particle moving like this, and B is also, that means the theta is 0. So no force will act on it, thus the particle will continue to move along the same path. That means it will have 0 acceleration because there is no force, so acceleration will also be 0. If the particle is moving perpendicular to B, just now we have seen it will follow a helical path. Okay, so it will if the particle is only moving, if the particle is moving along the perpendicular, so it will perpendicular to B, it will have the force, because here this is the particle moving and this is the B, so the angle between them is 90 degree. So that means sine 90 is maximum, that means the force experienced will be maximum here. The force experienced will be maximum here. And what is the force? This is the force, which is the maximum force which will act on the particle, because sine 90, if the particle is moving perpendicular to B, that means sine 90 angle is 90 degree, that means sine 90 is maximum, sine 90 is maximum, so the force will become maximum and it will have the circular motion, it will have the circular motion. Clear? Okay friends, let's see. Now another important topic which is called the Lorentz force, which is called the Lorentz force. Very, very important topic. Lorentz force. What is Lorentz force? Now see, we individually studied electric field force, behavior of particle due to electric field. We studied behavior of particle due to magnetic field. Now we will study behavior of the particle in both electric and magnetic field. Okay, so the force which is caused when a particle will travel in both electric and magnetic field is called the Lorentz force. So in the electric field we all know the force acting will be this, in the magnetic field we all know the force acting will be this. So Lorentz told the net force acting on the particle will be this. So this is the Lorentz forces definitions, and this is the formula for the Lorentz force. That means net force due to the electric and magnetic field. Net force due to electric and magnetic field. Clear? Now let's come to the special cases, because these are very important. Okay, so let's see. When V, B and E all are collinear, that means the particle moves like this, electric field is like this, magnetic field is like this. Please watch here. We know that when the particle is moving like this, already we have seen the magnetic force will be 0 and electric force will be maximum. Electric force will produce the acceleration. Okay, theta is 0 degree, right? Now if the particle is moving, parallel, then theta will be 0 degree, and if the particle is moving opposite to electric and magnetic fields, theta will be 180 degrees. Okay, so we know sine 0 and sine 180 both are 0 degree, 0. So here in case of electric field, as you can see, in the case of electric field, it will suffer as if the particle is moving along the electric field. That means it will have the maximum force produced and acceleration. But since it is traveling, and if the particle is traveling parallel to B, the magnetic force will be 0. Okay, speed, velocity, momentum, kinetic energy will change because there will be an acceleration due to the electric field, so they will change, but direction of motion will not change because the particle will continue to move in the direction of E. Okay, similarly, when V, E and B are perpendicular to each other, please next note here, when V, E and B are perpendicular to each other, in that case what happens? Net force is 0. We use here, please watch one thing. When the E, V and B are perpendicular to each other, please watch one thing, that in that case the force due to electric field and the force due to magnetic field will become equal. So this is the force due to electric field, magnetic field, and here is R, and the acceleration will be 0 because there is no net force, so there will be no acceleration. And this concept that when the particle is entering in electric and magnetic field, see here, this is the particle entering. Okay, so this is the electric field and this is the magnetic field. So magnetic field and electric, basically it looks like this: electric field, magnetic field, and this is the velocity of the particle. All are perpendicular to each other. In this case, please watch what happens is the force due to electric field and force due to magnetic field will be same, so we can tell there is no net force. The net force acting on the particle, net force will be 0, and if the net force is 0, then acceleration is 0. Acceleration is 0, and this is called velocity selector. That means I don't want that the particle should show any bend. And okay, so here, that is why you can watch here that the particle is entering the electric and magnetic fields, but it is coming out undeviated. It is coming out undeviated. Okay, it is entering through the electric and magnetic fields perpendicularly, but it will come out undeviated. So that is why this concept is called the velocity selector. This is called the velocity selector. Clear? Next, friends, we are going to learn another very important topic, that is cyclotron. Cyclotron. Okay, now what is a cyclotron? What is a cyclotron? See, please let me first give you the principle of cyclotron, which is very, very important. The principle of cyclotron, very important, working. Okay, so now let's first see what is a cyclotron. A positively charged particle can be, what is the principle in cyclotron? What happens? A positively charged particle can be accelerated to a sufficient high energy with the help of smaller values of oscillating electric fields by making it to cross the same electric field time and again with the use of a strong magnetic field. So please watch one thing. That means here we are telling that when a cyclotron is working, please watch here first. Let me. Okay. So in the case of cyclotron, what happens? I'm just telling you, there are two D's like this. Okay, there is the radius of the D. R. Here is a positive charge Q. Okay, we will provide, these are called D's. What are these called? These are called D's. Okay, so we will apply the magnetic field. We will apply magnetic field. Please let me draw it with the help of some other pen. Okay, so we will be applying here magnetic field. This is the magnetic field. Okay, B. And we will also be applying the electric field. Okay, so initially we will be connecting this plate to a positive terminal and this plate to a negative terminal. Okay, so see what happens. We have introduced a positively charged particle. What we will do? We will make this charged particle move around in alternative electric and magnetic field. It will move around alternately in electric and magnetic fields, oscillating electric, as you can see. Sometimes this will be plus, this will be minus, then this will be plus, this will be minus, then this will be plus. So the polarity of the two D's will keep on oscillating, plus minus, plus minus, plus minus, plus minus, like this. So what will happen? So this is called oscillating electric field. Now when the charged particle is placed between the D's, initially what will happen? It will get attracted to the negative D. Okay, so suppose this is D1 and this is D2. So the charged particle will first get attracted to the D1 because it's negative terminal and D2 is positive. So ion will get accelerated or attracted towards the D1. On reaching the D1, inside D1, the ion is at free field space. That means the ion will try to move freely. It will move with a constant speed inside D1. Let it be V. Now because there is an electric and magnetic field, so I told you, due to the electric field it will get attracted to the inside the D1, and due to the magnetic field it will make a circular path of radius R. So that means due to the magnetic field BQV force, a centripetal force will be provided and the charge will make a circular path like this. It will try to make a circular path of radius R. So what is that radius R? This is that radius R. So what is the time period of making that semicircular path? So what is the distance covered? Distance covered is pi r. It is not 2 pi r because it's a semicircle, so it is pi r. By the velocity, distance by speed is the time taken to cover this half circle. Okay, putting the value of r, we get this. Now this part is completely a constant. That means the time spent by the charged particle inside the D, either it is D1 or D2, should always has to be same. It has to be same. That means the time taken by the particle to cover the semicircular path is independent of both speed and radius. That means the time taken by the particle to cover that semicircular path should be constant, whether it is inside D1 or inside D2. So now what happens? When the particle is covering up the semicircular path, okay, then after it comes out of both of the D1, after it comes out of D1 into the gap, now this D2 will become the negative terminal, this D2 will become the negative terminal, and D1 the positive. So D2 will become negative and D1 the positive. First D1 was negative, D2 was positive, and now when the particle has come out here again after half circle, now D2 is negative, so the particle will get attracted towards it, and it will spend the same time inside this. Okay, it will spend the same time inside this, and this will continue, this process will continue. Okay, so the D's will continue to do plus minus, plus minus, plus minus, plus minus, and the ion will continue to move like this in D1, D2, D1, D2, D1, D2, but providing it is completing in the same time, because time is constant. So what happens here is, it will try to cover up this path, it will try to cover up this type of motion, but please watch one thing, as it covers up, it will gain more energy and the radius will go on increasing, radius will go on increasing like this. Okay, so due to this, its speed has to be increased, because it should spend the same time, so its speed will constantly go on increasing to a very high speed, and its energy will also increase. So the ion will be accelerated, and now it can come out of the D's, it can come out of the D's from here, the ion can come out of the D's like this with a huge speed and energy. The ion can come out of the D's through an opening here, there is an opening window, so this ion will come out with a huge speed and huge energy. So that means that in a cyclotron, as I told you, we can accelerate a positively charged particle to a high energy and speed, we can accelerate it. Okay, so as you can see, what is the energy of the particle coming out here? It will come out with a maximum velocity, it will come out with a maximum velocity. Okay, so the centripetal force will be this, and the magnetic force is providing the centripetal force, so this is the velocity with which it will come out. Clear? So what is the kinetic energy of that ion? This. Now we already know Vmax is this, so putting the values of Vmax, so this is the maximum kinetic energy of the charged particle, which will ultimately come out with a huge speed and energy. It will come out with a huge speed and energy. Okay, next is, what is the frequency of oscillation of the cyclotron? As I told you that the D's will continue plus minus, plus minus, plus minus like this. So what is that oscillation frequency? What is that oscillation frequency? So this is 1 by T, and time period already we found out. As you can see, we already found the time period here. This is the time period, so that means frequency of oscillation of the electric field, which is making it plus minus, is this. Now angular frequency omega is 2 pi by T, which should be this. So please note here, this is the frequency of oscillation of the electric field in a cyclotron. Frequency of oscillation of electric field in a cyclotron is this, and time period of oscillation will be this. Okay, this is the time period of oscillation of the electric field. Now limitations of the cyclotron. What we cannot do with a cyclotron? What we cannot do with a cyclotron? Number one, when an ion is accelerated, its mass never remains constant. Please watch here. We think that the mass is always constant, but in case of charged particles, mass which will always increase with the increase in the speed. Mass will always increase. So if the mass will increases, mass will never remain constant in case of a charged particle moving with a great speed. Mass, if the velocity of the particle increases, the mass of the particle will increase. And if the mass of the particle increases, how can the time period remain same? The time period cannot remain same. That means the frequency of oscillation of the D's, they cannot keep sequence with the electric field. As I told you, this is D1 and D2. Please watch here. This is D1, these are the D's. Okay, this is the D. Now there polarity oscillations, plus minus, plus minus, plus minus. Now the frequency at which they oscillate, the polarity, that frequency, with that frequency the charge has to move in to these, again this, again this, again this. But we know that since the mass will go on increasing, since the mass goes on increasing, so it cannot, the particle cannot maintain that same, it cannot synchronize or maintain the same frequency of oscillation with the D's. So after some time it cannot be, the speed cannot be increased beyond a certain limit. Please maintain that. The speed cannot be increased after a certain limit. The particle will stop. Clear? So next, let's see limitation. Cyclotrons are suitable for accelerating heavy particles like proton, deuterons, alpha particles, but not electrons, which are light particles. So cyclotron cannot accelerate electrons. Third, uncharged particles cannot be accelerated. I told you it has to be charged particles, either plus charge or minus, but please note here, it can only accelerate positive charge, not electrons. As I told you, electron is a negative charge, so cyclotron cannot accelerate a electron. Clear? Next, let us study force on a current carrying conductor placed in a magnetic field. So please watch here. This is a conductor of length L. Here is the current flowing, and let us take a magnetic field at an angle theta with the length of the conductor. Let us take a magnetic field B at an angle of theta, inclined at an angle of theta to the direction of the electric current. So what is the force acting on the conductor? F is given by, this is given by I L cross B, which is B I L sine theta. Please watch here. The force due to the magnetic field will be B I L sine theta, because this is B cos theta and this is B sine theta. So this component of the magnetic field will provide for the, as I told you that this is the charge moving like this, so this component of the magnetic field will provide for the force. Okay, F equal to B I L sine theta. This is the direct, this is the value of the force due to the current flowing through the conductor in a magnetic field, P I L sine theta. Now special case, please watch, let us see some special case. If theta is 0, or 180 degree, that means the magnetic field is either this direction or this direction. Theta is 0, so remember it, force acting will be 0. No force will act on a conductor. So if the magnetic field is in the direction of the current carrying conductor, no force will act. The current carrying conductor placed parallel in the magnetic field experiences no force. Please watch, this is a very, very important point, that if there is the current carrying conductor will never have any force. Current carrying conductor placed parallel to the magnetic field will experience no force. Clear? Similarly, if theta is 90, that means sine 90 is maximum. So maximum force will act on it. And what is the maximum force? This is the maximum force acting on the conductor. So when the magnetic field is perpendicular to the conductor, magnetic field is perpendicular to the direction of flow of current. Okay, the conductor is placed, see the magnetic field, if it is perpendicular to the direction of the current, then the force acting will be the maximum. Okay, and what is the direction of the force? We can use the Fleming's. Please note, very, very important, for finding the direction of the force. The direction of the force is given by Fleming's right hand screw rule or Fleming's left hand rule. This is the direction of the force, how you will be finding. Okay, so remember it, Fleming's left hand rule. He told that if this is the direction of magnetic field, if this is the direction of the current, then the force will be perpendicular to both the current and the magnetic field. So we have to use our left hand and we will place. So this is the middle finger, this is the forefinger, and the thumb will point to the direction. If we hold the middle finger, okay, this is the middle finger, that is the current. This is the thumb, this is the forefinger, which is the magnetic field. So he told that your thumb will now point in the direction of the force. So you have to place your fingers like this. Okay, so if we could place our left hand's finger, thumb, middle finger and forefinger perpendicular to each other, and if we know the direction of B and I can easily tell in which direction the force will act on the conductor. Okay, next is force between two parallel conductors carrying current. Please watch, this is a very, very important topic. Force between two parallel conductors carrying current. Force between two parallel conductors carrying current. So here is the two conductors. One is this, one is this. Okay, so please watch here. In this the current I1 is going up and in this also going up. So same direction. Okay, same direction. In this the current is going up and in this the current is coming down. So opposite direction. So we will study two different cases. Now let the two conductors be separated by a distance r. Let the two conductors be separated by a distance r. So watch here. The magnetic field due to this conductor flowing current I1. Current flowing is I1. So the magnetic field at a distance of r here, or the magnetic field at a distance, magnetic field due to the first wire at a distance of r is given by this formula. Magnetic field due to the first wire at a distance of r is given by this formula. So what is the magnetic field due to the first wire at a distance of r is this. Now here in the second wire we have the magnetic field, we have the current. So if we have the magnetic field, if we have the current, then we should have the force. So now force acting on the second wire will be this per unit length. Please watch here. This is called unit length. For every 1 centimeter of the second wire, what is the force acting is this. Okay, B1 magnetic field due to the first wire, current due to the second wire, and 1 centimeter. Okay, B1 I2. So putting the value of B1, we find that this is the force which is acting between the two wires carrying current I1 and I2 in the same direction, carrying current I1 and I2 in the same direction. Okay, so this is the formula of the force between the two wires carrying current I1 I2 separated by R. This is the force. And please remember one thing, that if the two wires carry currents in the same direction, so there will be an attractive force between the two. The two wires will attract each other. They will attract each other. Similarly, if the current flowing in the two wires are in the opposite direction, if the current flowing in the two wires are opposite direction, the two wires will repel each other. The two wires will repel each other. Please watch, note this thing, very, very important. Okay, this is the force due to the two wires. This is the force acting due to the two wires carrying current I1 and I2 separated by a distance. Now this force is what type? If the currents are in the same direction, they will attract each other. If the currents are in opposite direction, they will repel each other. So this formula is very, very important. Next, so let us see what are the important things here. Okay, if two conductors of length L and L, so please watch here. So there are two conductors of length, one is L, one is capital, carrying currents I1 and I2, okay, separated by R. So what is the force acting between them? We already know that the force acting between them is mu 0 by 4 pi 2 I1 I2 by this is the force acting, okay, on the second wire. Force on the long conductor is equal to the force on the short conductor. This is the force acting. This is, please note here, there should be, this is the force acting and this is the force per unit length. So into L, length of the wire is the total force. Next is force on each conductor is same in magnitude and opposite in direction. Please, okay. So that means if I F12, force due to 1 on 2 will be same as force due to 2 on 1. Okay. When two currents approach each other, please watch here, they are approaching each other. They are approaching each other towards a point. Approach each other or go away from that point. They are going away from that point. Going away from, if they are approaching, see, this is the approach. Please watch here. This is the approach. Approaching a point. Approaching. Then they attract. So approach is attract. So if the two currents are approaching a point or go away from a point, it will be an attractive force. Now, if one current approaches a point and the other leaves the point, then the force is repulsive. Please watch here. one will be approaching a point and one will be leaving a point. If so, if they will be repulsive. So watch here, this is leaving a point, and please watch here, this is leaving the point and this is approaching the point. So they will repel each other. They will repel each other. And if both of them approach or leave, see, both are leaving and both are approaching, so they will attract each other. They will attract each other. Please watch here. When the two charges Q1 and Q2 moving with velocities V1 and V2, so please remember here, this is a formula which you should remember. Now instead of the current we have taken charges. So suppose in the two wires the charges moving are Q1 and Q2 with velocity V1 and V2. So this is the formula between the two wires. Instead of this formula, current formula, we will use Q1, Q2, V1, V2. Okay. Another very important point is that, please watch here. Here is a wire which is having a weight of its own, hanging down, carrying current I2. Okay. Now in which direction should another wire carry current so that this wire is completely held like this? It will not fall off. It will not fall off. So if the wire is to be held, that means its weight should be balanced by, there is some force. Its weight should be balanced by some force, and that force should be attractive force. The weight should be balanced by a force, and now this force's direction is this. That means there should be attractive force between the two, and we know if there is an attractive force, the current should flow in the same direction. The current should flow in the same direction. So the force acting between the two is this, which should balance, this is the attractive force which should balance the weight of the wire. So this is the attractive force, as we all know. This is the attractive force which should balance the weight. Okay, it has to be in the opposite direction. So this has to be an attractive force, and when there is an attractive force, the current's direction should be same. So I1 and I2 should flow in the same direction. Okay friends, next is so now we are going to study torque on a current carrying coil placed in a magnetic field. Torque. Okay, so let's see here. This is a rectangular coil. This is the rectangular coil. Please watch here. This is the rectangular coil, and we are assuming that let the length of the coil be L and breadth of the coil be B. Let us assume this. Okay. Now we have taken a coil PQRS and we have taken it in a magnetic field. We have taken it in a magnetic field B. We have taken it in a magnetic field B such that B makes an angle theta with the coil, plane of the coil. B makes an angle theta with the plane of the coil. Okay. So now please watch one important thing, that is, let the current in the part PQ flow like this. So here it will be this. That means the cut, now they are separated by a distance B. That means if the currents are flowing in the opposite direction, there has to be a repulsive force, isn't it? There has to be a repulsive force. So the direction of magnetic field is this, the current is this, so direction of magnetic field is this, the current is this, this is the B, this is the I. That means a force will act on PQ, a force will act on PQ which should be in this direction. Similarly, on RS, the magnetic field is this, the current is this, so the force acting on this should be this. Now these forces acting on PQ and RS are in opposite directions. These forces acting on PQ and RS are in opposite directions. So what will happen is that they will cause a turning effect and the coil will turn. So please watch here. This is the breadth of the coil. This is the breadth of the coil. Okay, B. So this is B cos theta. This is the magnetic field which is making angle theta with the coil. If this is theta, this is theta, this is B cos theta. Clear? So now what is the force acting? What is the force acting on this part? Force is BIL, and here also force is BIL. Okay, this direction of force. Now force acting is BIL, as I know that. Now what is the torque? Torque is force into perpendicular distance. So force into perpendicular distance is B cos theta. Force into perpendicular distance, which is B cos theta, which is BIL B cos theta, and L into B is the area of the coil. So BIA cos theta. Now if there are n number of turns of copper wire, if we have n number of turns of copper wire, okay, so what we will do is that we will multiply this, torque will increase n times. Now please watch one thing. Please watch one more important point. That is, this is the plane of the, this is the normal to the coil. This one is the normal. This is the magnetic field B making angle theta with the plane of the coil. So what, let this be alpha. Now we know this angle is 90. So I can write alpha plus theta should be 90. That means theta is 90 minus alpha. So instead of the theta, we can write 90 minus alpha, and cos 90 minus theta will become sine alpha. So this is our one of the most important formulas of torque. And please note here, this alpha is the, this is the direction of B. This alpha is the normal angle of the normal with the direction of B. Alpha is the angle made by the normal of the this plane, okay, with the B. So this is sine alpha, and theta was the angle with the plane of the coil with B. So please don't confuse. If you use this formula, if you want to use with the plane of the coil, then use this formula. If you want to use normal with the magnetic field, then use this formula. Here NIA is called the magnetic dipole moment. Please note here. So in place of NIA, we will put M. Now this, due to this torque, the coil will rotate in its axis. The coil will rotate like this. The coil will start to rotate like this. Okay. So now let us discuss some special cases which is coming out. Number one, if the coil is set parallel to the magnetic field, if the coil is parallel to the magnetic field. So please watch one thing. if the coil is parallel to the magnetic field, the alpha will be 90 degree. If the coil is if this plane is with the magnetic field, okay, so the normal will come out. That means this is the magnetic field, so my coil is like this, so the normal will be like this. So alpha will be 90 degree. So the torque acting will be maximum. Torque acting in that case will be maximum. Clear? Similarly, if the coil is set with its plane perpendicular to the magnetic field, that means this is the magnetic field and the coil is placed perpendicular to the magnetic field, that means this is my normal. So the normal is making an angle 0 degree, so the torque will be minimum, which is 0, because sine 0 is 0. Sine 0 is 0. Okay friends, let's move on to the next topic, which is the moving coil galvanometer, another very important topic for this particular chapter. Moving coil galvanometer. Okay, so what is there in that? Let's see what is there in the moving coil galvanometer. After the theory, we will also discuss some numericals, so please keep following the class properly. It is used for detection and measurement of small currents. Moving coil galvanometer is used to detect small current. So here we see there are two magnets, North Pole and South Pole. North Pole, South Pole. Two magnets are there. Clear? We have placed a rectangular coiled PQRS suspended by a phosphor bronze strip. Through which we will send the current I. Current will be sent like this. So when the current will pass through this, as we already studied previously, that whenever current is flowing through a coil placed in the magnetic field, there will be a torque acting on it, which will turn it, which will rotate it. Clear? So watch. So due to the rotation of that, okay, due to the deflection of that, we can measure small currents of it. Now what is the principle of this? Principle, please watch. Principle says that when a current carrying coil, this is the current carrying coil, current is coming like this. When a current carrying coil is placed in a magnetic field, it experiences a torque. This is the main principle. Okay, so let the length of this coil be L, the breadth is B. What we have all studied this previously. So let there be n number of turns. We have already studied that the torque acting on this coil should be this. Torque acting on it. Okay. Now if the coil makes 90 degree, the normal makes 90 degree with the magnetic field. That means the coil is parallel to the magnetic field. This is the plane of the coil. Magnetic field is like this. Normal is coming out like this. So the angle is 90 degree. So the maximum torque will act on it. Maximum torque will act on it. Now due to this maximum torque, the coil will rotate and the wire will get twisted. This strip will get twisted. Let it get twisted by an angle theta. Now when it get twisted, it will again rotate back. So let the restoring torque per unit twist be K. So this torque is balanced by a restoring torque, which will again bring back this torque is balanced by the restoring torque, which is K theta. This will get twisted through an angle theta. Okay. due to which again it will come back like this. So the rotation of the rectangular coil is balanced by the restoring torque k theta. That means this should be equal. And what is K? K is the restoring torque per unit twist. K is the restoring torque per unit twist. Please note here. So from here we get this formula. And since K by NBA, these are constant, we take it G, which is called the galvanometer constant. So we can see that the current which we will pass through the galvanometer is proportional to the twist produced by the wire. Okay, so more the current you pass, more the deflection. So more the deflection, more the current it can measure. So this is how the moving coil galvanometer also works. Let's see here. Next important topic, which is called the current sensitivity. The current sensitivity and voltage sensitivity, very important. It's a very, very important topic. Okay, so let's see what is it. It is the angle of twist divided by the current passed. That is called current sensitivity. So theta by I, which is this. Okay. Voltage sensitivity is theta by V, and V is equal to IR. I is the current passed, R is the resistance of the coil. So now theta by I is called the current. Theta by I, as we have already known, is this. So it is IS by R, current sensitivity by the resistance of the galvanometer. Next is conditions for sensitive galvanometer. What is sensitive galvanometer? A galvanometer which can measure very small magnitudes of current also is a sensitive galvanometer. Okay. If it shows large deflection even when a small current is passed through it, that is called sensitive galvanometer. So this is the formula of theta. Now how can we make the theta large? To make it sensitive, we have to make the theta large. Theta we have to increase. Okay, so how can we make the theta increase? So either I can increase the n number of turns, but number of turns cannot make it beyond a certain limit. Number of turns of the coil cannot be increased. So this is the rectangular coil PQRS. Okay, you cannot increase the number of turns of copper wire here. Beyond a certain limit you cannot do that. So we cannot rely on increasing the number of turns. B is increased by using a strong horseshoe magnet. That we can do. We can increase B. A cannot be increased because A is the area of the coil. We will make a larger area. So larger area will make the whole apparatus very bulky. So we cannot do that. K, which is the restoring torque per unit. Okay. So K can be, if I decrease K, so we will choose either quartz or phosphor bronze strip, which has a very, very low K. So if the K is less, so theta will be more, and if theta will be more, sensitivity of the galvanometer will increase. So next topic is shunt. What is a shunt? It is a low resistance connected in parallel with the galvanometer or ammeter. It is a low resistance connected in parallel with the galvanometer or ammeter. So please watch here. Shunt. So this is the shunt connected parallel to the galvanometer. It is a low resistance. It is very low resistance connected in parallel to the galvanometer. Clear? Now what it does? It protects the galvanometer or ammeter from strong currents. It will protect the whole galvanometer if any by chance high current is entering the galvanometer. So galvanometer will not burn out. This will give a protection. If I be the total current, so watch here please. In the figure, let's get started. Let I be the current flowing. The galvanometer can take maximum value is Ig. Suppose this is 2 ampere, but I want to measure 5 ampere. So what should I do? The remaining 3 ampere should pass through this. That is why we are using a low resistance, because ultimately, see how to increase. I want to increase the capacity of this. Okay, this galvanometer can take only 2 amperes. That means we can measure very small current. But suppose if I want to measure a high current, so if I want to pass 5 ampere through this galvanometer will burn out. So what to do? Then I have to connect a low resistance in parallel so that the balance current can pass through it. Okay, that means I minus Ig will pass through this. That means my total current I is Ig plus Is. Is is this or Ig is this. Now we know, because these two are in parallel, so the potential across this and this will be same. So it will be Is into S and this will be Ig into G. They should be same. Is is I minus Ig. So we get one formula. This is the current flowing through the galvanometer and this is the current flowing through the shunt. Okay, please keep this in mind. How to make the galvanometer work as a high current measuring instrument. Okay, high current, we have to allow a low resistance in parallel to the galvanometer. We have to allow a low resistance in parallel to the galvanometer. The balance current will pass through the low resistance. Okay, so instead of measuring only low current, we can also measure high current, because the balance of the current will pass through this. So this instrument will take out the balance of the current, as I showed you. So this is how we can use it to measure a high current. Uses of a shunt. Okay, where do we use a shunt? Number one, to protect the galvanometer from strong currents, to convert galvanometer into ammeter. It is used for increasing the range of the ammeter. I told you that initially we were measuring 2 ampere and now when we connected the shunt we can measure 5 ampere, 10 ampere, anything. We converted this to measure large currents also. Similarly, what is an ammeter? Please watch here. Ammeter. So an ammeter is a low resistance galvanometer. So same thing, see, this is a low resistance. It's the same thing what we are doing actually. This is the low resistance connected to the galvanometer. Same formulas. So what is the total resistance? This is the total resistance because they are in parallel. Okay, it is used to increase the current capacity of the galvanometer. So same thing, it is the same thing. Next, let us see. Please remember this. This is very, very important, that an ideal ammeter has zero resistance. Very, very important. Short MCQ question. An ideal ammeter has zero resistance. Very important. Ideal means a very, very super fine ammeter will have zero resistance. Second is, what is a voltmeter? A voltmeter is a high resistance. In a voltmeter, what happens is just the opposite. It is a high resistance connected in series, okay, used to measure potential difference between the 2 points. So suppose we take it like this. So this is that high resistance. So current is flowing like this, Ig. Okay. So what is the total potential now it can measure is Ig. R plus G is the total resistance. So Ig, this is the total potential it can now measure. Initially it was only like this. So it can measure potential of only Ig into G. And now see, we used a high resistance. So now we can measure a larger potential. And this is the value of the high resistance which we have connected. Okay. And total resistance is this, because it's connected in series. An ideal voltmeter has infinite resistance. For an ammeter, the ideal ammeter has zero resistance, and for a voltmeter, an ideal voltmeter has infinite resistance. Clear? Okay friends, so with this we move on to the numerical part of the chapter. So let's get started. What is the radius of path of an electron, mass of the electron given, charge of the electron given, speed of the electron given, and magnetic field B given, perpendicular to it? So this is the B, the charge is entering perpendicular to it. So they are telling what is the radius. So we know the force acting, centripetal force provided will be this, because it is entering perpendicular. So theta is 90 degrees. So the formula comes out to be this. Okay. So from here we separate R, we put the values, we get the radius. So when a charge is entering like this, it will cover up circular paths like this. Okay. Cover up circular path. So what is the radius of this? This is the radius of the path. Now they are telling frequency. Now it is covering 2 pi r with a speed of this. Okay. So we know frequency equal to V by 2 pi r. So frequency we find out, this is the frequency. Kinetic energy is half mv square. Putting the value of m and v, we calculate the kinetic energy of the electron. Next friends, let's see the next sum. A proton is traveling with a speed of this. So this is the horizontal velocity of the proton, Vx. Calculate the transverse deflection in traveling horizontal distance 5 centimeter in electric field. That means they are telling this is the electric field along the y-axis. What is this is the distance traveled along the x-axis, 5 centimeter. Okay. They are telling what is that deflection which is produced here due to the electric field. So first of all, we know that to cover this time, the horizontal speed always remains constant. So we will take this horizontal speed and this as the distance and find out the time taken to cover the horizontal, because this is the same time. In the same time it will rise this much, at the same time it will rise this much. So it has only the horizontal velocity, so vertical velocity was not there. Now using this formula, this is 0, and we know that force is Q into E, so acceleration will be force by mass. So using these, time already we know. Okay, so we can calculate the vertical deflection of the path of the proton. Next, a stream of electrons traveling with a velocity, this is the velocity of the electron, is deflected in passing through electric field of this. This is electric field given perpendicular to its path. That means the electric field is perpendicular to the path of the velocity. So it will move like this. So if the radius of the deflection is 3 meter, that means this is the radius of deflection, 3 meter. Q by M we have to find. So we know force, electric force is QE, which is providing the centripetal force. So they have given the radius, mass. So we will now separate the Q by M, which we have to find. Everything given, we can find out the value of this. Next, okay, an electron is moving. So friends, an electron is moving southwards. This is the electron moving southwards. Okay, velocity given, magnetic field directed westward. That means they are perpendicular, so they will make a circular path. Okay, so force acting on the electron is BQV sin theta, and theta is 90 degree. We know that. So this is the force acting due to the magnetic field. We can find it. Next, they are telling an electron is having an energy this much, 2000 electron volt. Describes the circular path in a magnetic field. This is the B given, magnetic field given, radius they are asking. So again it is BQV equal to mv square by r. So r we have to find, put the value of m, velocity given, b given, q given, so we can find out the radius. Okay, now they are asking what is the radius of the path. So from here, first of all, what we will do, so see, we need the velocity here, we need the velocity here. So they have given that the kinetic energy of the electron was 2000 electron volt. Now 1 electron volt is 1.6 into 10 to the power minus 19 joules. Please keep note here. So multiplying this, so this is the kinetic energy, mass we know, velocity we can find. Putting this velocity's value here, we can calculate the radius of the path of the motion of the electron. Clear? Okay, an electron is accelerated through a potential. This is the V given, magnetic field B given, perpendicular to its direction. So again see, there is an, this is the energy, find the radius of the path. Now this is the potential difference given, V given. So what is the energy of the accelerated electron? E into V. Remember it, energy is also given as E into V, so which is half mv square. From there we find out the V, and now because it is in a magnetic field perpendicular, it shows this is the B, it is entering, velocity is perpendicular to it, so the force acting will be BQV, which will provide the circular motion, and from there we can find out the radius of the path of the circular motion. Okay friends, now this is a very interesting sum. There are 3 particles, proton, deuteron and alpha particle. So let's first see what is a proton. Proton is a hydrogen 1,1. What is a deuteron? Deuteron is a hydrogen 2,1. What is an alpha particle? It is a helium 4,2. Okay, so please watch here. They told that the kinetic energies of the proton, deuteron and alpha particle are same. So kinetic energy is half m p vp square half. Now the deuteron, you can see that mass is twice of the proton, so 2 mp, and here mass is 4 times of the proton, that's why 4 mp. Okay, so we are getting, so let all the kinetic energy be equal to k. So from here we are getting Vp square is this, Vd square is this, V alpha square is this. Clear? Now we have to find out what is the force, magnetic force acting on the proton due to the magnetic field is, we know that due to magnetic field the force acting is BQV equal to mv square by r, because magnetic field will make you move in a circular path. So applying it for a proton, radius of the proton is this for the proton, radius of the circular path due to proton, radius of the circular path due to the deuteron, radius of the circular path from here due to the, this is radius, sorry, circular path due to the alpha particle. Now we have to compare their radiuses, so that means we are comparing this part, these 3 values we will compare. So we can see that all things cut out, so we get it here. Now Vp, what remains is Vp is to 2, Vd is to 2 V alpha. So we know Vp is root over kmp, this is this, so all the common things cut out, what remains is this. This is the ratio of the radiuses of the proton, deuteron and alpha particle. Clear? Let's see the next sum, friends. There is a long straight wire AB. AB is a long straight wire carrying a current of 4 ampere. As you can see, a proton P is traveling at a speed. This is a proton P traveling at a speed, given speed of the proton given. It is moving parallel to the wire, as you can see this, which is 0.2 meter away. Proton is 0.2 meter away and moving parallel to the wire in a direction opposite to the current. So if this is the current, the proton is moving like this. Okay, find the force. So because this is the current, okay, so what will happen, there will be a magnetic field due to a straight wire is given by this formula. Magnetic field due to a straight wire is given by this formula, and please remember mu 0 is 4 pi into 10 to the power minus 7. Please note this value. So using the values, putting the values, current I know, distance here r is the 0.2. Using this we are getting that the magnetic field acting on the proton will be this. Now force acting on the proton is given as BQV sine theta. See the direction, it is 90 degree. So putting the values of BQ is the proton which charge is given, velocity of the proton is given, putting this we get this. And now applying Fleming's left hand rule, this is the force acting, this is the magnetic field. So this is the proton which will come out of the paper, perpendicularly out of the paper, perpendicularly out of the paper. Okay, the direction of the motion of the proton will be perpendicular out of the paper. Please remember it, whenever a current is flowing like this, there will be a magnetic field whose direction will be like this. So direction of B is like this. Okay, means basically it will be like this, tangential. Proton is acting perpendicular, so force should be parallel, perpendicular to both. So this is the force acting on the proton. Clear? Next, So let's see, friends, the next sum. What is it all about? Cyclotron oscillator. There is a cyclotron which is oscillating with a frequency of 10 megahertz. Cyclotron is oscillating with a frequency of the cyclotron is given to us. Mega means 10 to the power 6, so this is the frequency. What should be the operating magnetic field? B, I don't know. For a proton, we know cyclotron can accelerate only positive particles, that's why protons. Radius of the D, which is R, given. Okay, so let's see. Frequency I know, so time period is 1 by frequency. So we know that in a magnetic field it will follow the circular path of radius R, okay, and speed is V. So it will cover 2 pi r in a time t. So what is the speed? We are calculating the speed. Now from here we are putting the value, and the force acting due to a magnetic field will provide the necessary centripetal force. We have done this. Cutting one V, putting the value of V here, and putting the values whatever we know. We are calculating the value of the B. This is the value of the B. And now kinetic energy is half mv square. This is the value of V. Okay. Radius and everything is given to us. Radius is 60 centimeter given to us. Radius of the path is 60 centimeter. This radius is given to us as 60 centimeter. We are able to calculate the kinetic energy of the particle. Kinetic energy of the particle. Clear? First we will calculate this in joules, then we will divide it by 1.6 10 to the power minus 13 to get it in million electron volt. We will then divide it with 1.6 10 to the power minus 13 to get it in million electron volts. Clear? So let's see. An electron beam passes through a magnetic field. This is the magnetic field given, and electric field given, both acting together. So we know when electric field and magnetic field are there, then this is the formula, they will be equal. From here we calculate the velocity of the electron, and now the force due to the magnetic field is only making it move in a circular path. So BQV will be mv square by r. VV cuts, so we can calculate the radius of the path of the electron. Next, friends, there is a straight wire. This is the wire whose weight is hanging down. No, question is, the length of the wire is given. It is carrying a current of 2 amperes. It is carrying current of 2 amperes suspended in the air. What is the magnitude of the magnetic field I should act so that it will remain suspended? So to balance the weight, I know the force should act, magnetic force should act up, and magnetic force due to a current is BIL. So BIL should be equal to mg. From there I will calculate the value of B. Similarly, friends, the Earth's horizontal component magnetic field is given to us. Earth's magnetic field is given to us, and direction is from south to north. As you can see, the magnetic field's direction is from south to north. Current is flowing from east to west. There is a straight conductor. This is the conductor. Current is flowing from east to west, 1 ampere current. What is the force per unit length on it? Now we know force on a current carrying conductor due to a magnetic field is given by this. Because I and B are perpendicular, so it is sine 90. So we calculate putting the values of B, I, and the length of the conductor is given to you as 1 meter. They have given per unit length, per unit. That means length I have to take 1. So we calculate this is the force acting on the conductor. Now they are telling if the current direction is reversed, south, if the current is flowing from south to north now, south to north, and we know when this current is acting along the B, that means the angle is 0 degree. So F is BIL sine 0. So force acting on the conductor will be 0. 0 force will act on the conductor. Now see friends, there is a conductor here. This is the conductor here, whose weight is hanging down. It is supported by two strings. So there is a tension T1 and T2. Now this conductor is carrying a current 5 ampere like this. This conductor is carrying a current of 5 amperes. They are telling that what is the magnetic field, what magnetic field should be set up normal to the conductor, what magnetic field should set up. So I should set up a magnetic field like this. Force due to magnetic field should be like this. To make the tension in the wire 0, that means this force should now balance the weight, so there will be no tension. So that means the force due to magnetic field should balance the weight. So I can calculate the magnetic field. Now they are telling what is the total tension in the wires if the current flows like this, the direction of the magnetic field will be like this, and the force will now come down. So the tension will now be F plus mg. F plus mg. So the tension will now be increased. If the direction of the current is reversed, the direction of magnetic force will also be reversed. So total, the tension will now be F plus mg. So there is a conductor of length 2 meter, as you can see. AB is a conductor of length 2 meter carrying current 2 ampere. It's carrying current 2 ampere. 2 meter is the length of this wire, parallel to an infinite. This is the infinite wire carrying current 10 ampere in this direction. Distance is 100 millimeter. This is the distance given, R, 100 millimeter. Force, what is the force? Now we already know that magnetic field due to this 10 ampere on AB will be this. So putting the value of mu 0 is 4 pi into 10 to the power minus 7, putting the value. I1 is 10 ampere, distance is 100 milli, so 10 to the power minus 3. So this is the magnetic field on this wire due to this 10 ampere. So what is the force acting? Force will be BIL. BIL. L is the length of this wire AB, 2 meter. Current flowing through the AB, 2 ampere. This is the B due to the first wire. So because the currents are flowing in the same direction, so attractive force, I already told you that if the currents are flowing in the same direction, it is the attractive force acting on the two wires. Okay friends, so let's see the next sum. This is a rectangular wire, and here is a wire XY carrying current 25 amperes. This is 2 centimeter away, this is 10 centimeter. So basically this is 12 centimeter away. Clear? Okay. They are telling what is the net force acting on the loop. So first of all, see, if I take due to AD, now AD is carrying current in this and this is carrying current in this. So these two forces will be attractive forces and the distance will be 12 centimeter. So this is the formula of the force between two. L1 is the length of PQ, L1 is the length of AD, L1 is the length of AD. So putting the values, we calculate this force is attractive because current is flowing in the same direction. Next, due to BC, current is flowing in the opposite direction with the wire. So this is the force acting between BC and XY. This is between BC and XY. So this will be a repulsive force because current is flowing in the opposite direction. I1 is the current in the XY, I2 is the current in the BC, L2 is the length of BC, and R is the distance between the two wires, which is 2 centimeters. So putting the values, we get this is the repulsive force. So see, repulsive force is more than the attractive force, so the net force will be repulsive minus attractive. So the net effect will always be repulsive. This is repulsive in nature. Okay friends, so let's see the next sum. There is a long straight wire PQ. So this is the PQ carrying current 60 amperes in this direction. There is a wire XY carrying current I in this direction. So please note it here that I current, this is flowing in this is flowing. So there has to be a repulsion. Okay, repulsion will be there. So what is the repulsive force? As we all know, per unit length, it is this. So putting the values of mu 0, this is mu 0, I1, I 2 pi, and R is the distance between 4 millimeter. So we calculate this much I. Okay. Now this is the force per unit length. This should balance the weight of the wire mg, mass per unit length. Okay, so this is given. See, mass per unit length of the conductor is given 10 to the power minus 2 kg per meter. So this force per unit length should balance the mass per unit length. So LL will cut. So then from here I can calculate the I. Okay friends, so next see 100 turn closely. This is the 100 turns. So these are 100 turns. Radius 10 centimeters. So the radius, this is the radius R. Carries a current of 3.2. So the current coming through this is it carries a current of 3.2. So the current it carries is 3.2 ampere. What is the magnetic field at the center? We know at the center the formula is this, mu 0 I by 2R, and because there is number of turns is n, so into n. So putting the values, we get magnetic field at the center. Magnetic moment is NIA. Magnetic moment is NIA. N is 100. I given 3.2. Okay, and area is pi r square. Remember, this is a circle, so pi r square. So we calculate the magnetic moment. There is a magnetic field being applied 2 Tesla in a horizontal. See, this is the magnetic field applied in a horizontal direction. The coil has rotated through an angle of 90 degree under the influence of the magnetic field. So the coil is rotated through 90 degree. When this current carrying coil is placed in the magnetic field, it rotates through an angle 90 degree. Okay, question is, what are the magnitudes of the torque on the coil in the initial and final? Initial, it was making how much? 0 degree. So this was the formula of the torque acting. So sine 0. So initial torque acting was 0, and finally it made 90 degree. So the final torque acting will be this. M is the magnetic moment, already we calculated. This is the final torque. Now they are telling what is the angular speed. We know torque is equal to I omega, where I is the moment of inertia which is given to us. So omega can be torque by I. So we calculate it is this much radians per second. Next friends, let's see a circular coil of 100 turns. This coil has 100 turns, radius 10 centimeter, carries a current of 5 ampere. This coil is carrying current 5 ampere, suspended vertically in a uniform horizontal magnetic field. This is the magnetic field, and the plane of the coil is making an angle. So watch please here. The field lines make 60 degree with the coil, with the plane of the coil. That means this magnetic field is making 60 degree with this coil, 60 degree, and this is the normal of the coil, so it should make 30 degree. It should make 30 degree, and we know formula of the torque is NIAB sine alpha. Alpha is the angle normal making with the magnetic field, which is 30 degree. So putting the values, we get the torque acting on it. There is a rectangular coil of area. The area of the coil is given to us. Number of turns is N. The coil is in the radial horizontal. Magnetic field 90 Gauss. Now 1 Gauss is 10 to the power minus 4 Tesla. What is the torsional constant of the hair springs connected to the coil? Current flowing is 2 milliampere and angular. So this is the theta. So here see, we know in a rectangular coil the torque acting is NIAB, due to which the wire twists. So that is K theta. So here we have to find the value of K. N I know, A I know, area I know, magnetic field I know, theta is 18 degrees. Putting the values, we get the torsional constant. As I told you, this is the rectangular coil. So when current will pass through it, it will rotate. So this will twist through an angle theta. So that is why K theta should balance the torque. Okay friends, next is the next sum. Current sensitivity of a moving coil galvanometer is increasing by 20%. So current sensitivity is theta by I, which is NBA by K. Let it be called as M. So this current sensitivity M has now increased 20%. So that means it is 120 by 100 of M, which is 6 by 5 of M. 6 by 5 of M. That means this is the new current sensitivity, because this M has increased 20%. That means it has become 6M by 5, and M is NBA by K. This is the new current sensitivity. Now voltage sensitivity is theta by V. V is IR. V is IR. So theta by IR. So let's see here. Okay friends, so here as you can see, the new current sensitivity has become 6 by 5 M, and M is what? NBA by K. Voltage sensitivity is theta by V. So theta, V is what? V is IR. So this is my current sensitivity, which I have taken as M. So it is M by R. Okay. Now new voltage sensitivity. So I have to use the new current sensitivity. And they told that the resistance has increased by a factor 2. So it will become 1 by 2R. Instead of R, I will take 2R. So this is my new voltage sensitivity. And this was my old voltage sensitivity. So what is the decrease? This is the decrease. So what is the percentage decrease? Decrease by original into 100. 40% is my answer. Clear? Okay friends, a galvanometer has 30 divisions. Current sensitivity of 20 microampere per division. For every one division, what is the current flowing? 20 microampere. So if there are 30 divisions, the galvanometer can take how much current? 30 into 20 into 20 microampere, which is, this is the current galvanometer can take. Galvanometer IG. But I want to measure 1 ampere. So see, this is a very small current, but I want to measure a high current. That means the rest of the current should pass through the low resistance in parallel. So we know IS into S equal to IG into G. potential of this and potential of this should be same because they are parallel. In place of Is, I will write I minus Ig. This is the current. Ig goes here. So how much current will go? I minus Ig. I minus Ig will go here. So from there, S is this. So Ig I know. G is the resistance of the galvanometer. I is how much current I want to measure. This is Ig. We calculate. This is the resistance. Low resistance I have to connect in parallel. Clear? So what is the net resistance? They are in parallel, so I will use this formula and I will calculate this. S and G both I know. I will calculate the net resistance. Now they are telling that how will you convert this ammeter? This ammeter means now the galvanometer has a resistance of this. This I want to convert to an ammeter to measure 1 volt. Okay, so that means voltmeter means I should connect a high resistance in series, and using this resistance of the galvanometer, because they told you have to convert this ammeter now to voltmeter. So G dash I know, so I have to measure 1 ampere current. So I equal to R plus G dash. Voltage I want to measure is 1 volt. Current sending is 1 ampere. R I don't know, G dash I know, so we can find out the R. Now see friends, here there are two resistors 400 ohms and 800 ohms connected to an ammeter of 10 ohms. So what is the total resistance? 1210 total resistance. So what is the current flowing due to the 6 volt? V by R, this. Now they are telling that if you connect a voltmeter of 10,000 ohm here across 400, okay, what is the potential across A and B? Okay, so first of all find out the total resistance of 10,000 and 400. They are in parallel, so using this is the resistance we calculated. Now this plus 800 is in series, so this is the total resistance of the circuit. So what is the current flowing in the circuit? It will be V by total resistance, and we find out the total current. So if this is the total current, the potential across AB should be the current into the net resistance, which is this. So this is the potential across AB. So friends, with this we have come to an end of this chapter. It was a very, very big chapter, and I hope that you have understood this chapter. So my request is, please go through the chapter, please pause the chapter, go through it very slowly, then only you will be able to understand it, otherwise not. I have completed the full syllabus, full of this chapter, including the numericals. I have also covered up the numericals of this chapter. So my request is, you don't have to basically make any notes of it. You can practice from numericals from any book, but regarding notes I have covered everything here. Okay, so you don't have to make any personal notes of your own. Just read the things which I have mentioned here, and all the things, all the important, the conceptual things are also discussed, so you don't have to manage anything of your own. So this is Parijat Sir Classes. Please watch, like, share and subscribe my channel. Okay, so till then we again will meet for the next class again. So it's good night and good evening or good morning, whatever it is from my side. Thank you so much.